I've been in networking for over a decade and decided to make some content to try to help others understand this industry. So let's talk about the subnet mask. So a subnet mask is paired with an IP address or a network ID to derive other pieces of information about the network. But before we can get into that whole process and how that works, we first need to understand what the subnet mask is. So the subnet mask, it's a 32-bit value that is represented very similar to an IP address. It has 4 octets, and there are 8 bits in each one of those octets. It's separated by a decimal point, and the numbers for each octet are a decimal value from 0 to 255, since the highest decimal value you can get with 8 bits is 255. So a subnet mask, it differs from an IP address in that from left to right, the bits themselves are a sequence of ones and then a sequence of zeros. So at no point in a subnet mask, by definition, can you have a 1 after a 0. So the first example here, you can see you got a whole string of ones there. And then in that third octet, there's a 0. And then everything after that's a 0. The example below that, we kind of flip those bits to just show that in that third octet, you have 110, and then when there's a 1 after that 0, that is an invalid subnet mask. All right, so it has to be ones, and as soon as you hit a 0, it has to be all zeros after that point. You cannot have a 1 after a 0 in the subnet mask. Now, because of this, it means that the bits have to follow a very specific pattern. So we have 8 bits, and here we have all 9 options that you can have for that 8-bit pattern for each octet. So it can be all zeros, that's fine because there isn't a 1 after a 0. You can have a 1 and then 7 zeros, 2 ones and then 6 zeros, 3 ones and 5 zeros, on and on until you get to all 8 ones. These are the only values that you can have in a subnet mask octet. These are the only valid ones. So let's do a quick review of the binary place values for these 8 bits, and then we're going to calculate the decimal value that can be in each octet. So the binary number line for 8 bits, if we're going from right to left, from low to high, it goes 1, 2, 4, 8, 16, 32, 64, 128. Now remember, the ones for a subnet mask go from left to right, not right to left. So if we look at this first example, we have all zeros in for every bit in the sub for that octet. Sorry, and when you have all zeros, that is converted to a decimal value of 0. So that one's pretty straightforward. All right, the next one down here, we have a 1 and then 7 zeros after that. So we put a 1 in the 128's place, and then we convert that to decimal. That's going to equal 128. So that would be the decimal equivalent of a single 1 and then 7 zeros after that. So below that, we have 2 ones and then 6 zeros. So now we have a 1 in the 128's place and a 1 in the 64's place. That means we have to add 128 plus 64, and then that gives us 192. Next, we have 3 ones. So there's a 1 in the 128s, the 64s, the 32s. Now, we've already added up 128 plus 64. We know that's 192. So all we're really doing is adding 32 to 192, and that gives us 224. The next one after that, we add 16 to that 224. We don't need to add up 128 plus 64 plus 32 because we already know that that's 224 from the previous one. So 224 plus 16 gives us 240. And then we add 8 to that. So 240 plus 8 gives us 248. And then we add 4. So 248 plus 4 is going to give us 252. And then 2 is our next place value. So 252 plus 2 is going to be 254. And finally, when we add that 1 to it, then if we have all ones in that octet, then that's going to be equal to 255. So now that we know all possible decimal values that a subnet mask octet could be, remember though that the rule about not having a 1 after a 0 it applies to the entire subnet mask and not just to an individual octet. So here's some examples. We need to represent all 32 bits here of the subnet mask. So in example 1, the place where the bits switch from ones to zeros, it happens in that 4th octet. And we can see that because it isn't a 255 or a 0. A 255 means that the octet is all ones. A 0 would mean the octet is all zeros. So there's only one place in the subnet mask that we could possibly have a value that is not 255 or 0. Example 1 shows that in the 4th octet, we have a 192, which means the first 2 bits are ones and then the last 6 bits are zeros in that 4th octet. So for example 2, the 3rd octet is where the bits switch from ones to zeros. So that means that the 4th octet has to be all zeros because that 3rd octet is where that switch happens. Example 3 shows where that switch would happen in the 2nd octet there. So you can see the 1st octet is all ones, so that's a 255. The 2nd octet is 254. That's not a 255 or a 0, so the bits switched here. We went from a 1 to a 0 somewhere in this octet, and that happens to be the first 7 bits are going to be all ones, and then the 8th bit in that octet is a 0, which means everything after that for the rest of the subnet masks has to be zeros, so octets 3 and 4 are then all zeros. And then the last example here, we have where the switch from ones to zeros happens in the 1st octet, which means octets 2, 3, and 4 have to be all zeros. Now, you don't have to have a 0 in the subnet mask. The definition is that you cannot have a 1 after a 0. So example 5 here, if I have all ones, 255.255.255.255, that's a valid subnet mask because I don't have any ones after zeros. Example 6 is the opposite of that, where I don't have any ones, it's just all zeros. Well, again, I don't have a 1 after a 0, so a subnet mask of 0.0.0.0, it's still a valid subnet mask. It still follows those rules. The other thing I want to highlight is that transition from 1 bits to 0 bits, it can happen at the octet boundary as well. So example 7 shows where we have the first 3 octets are all 255, so they're all ones. And it's the transition from the 3rd octet to the 4th octet is where that switch happens. So the last octet is going to be all zeros at that point. So that's where it switches right at that boundary of the octet. And that's still a valid 1. We don't have a 1 after a 0 in that subnet mask. So the whole point of remembering the octets and stuff is to tell us how many ones there are in the subnet mask and where that transition happens from zeros to ones. The reason that we represent these as decimal values is because it's just easy for humans to read that and understand it. Computers don't really care. So keep in mind that anytime we're dealing with subnet masks, we're dealing with 32 bits. There is no decimal there. There's no octet when it comes to the actual logic of it. That's just to help us understand what's happening. So another way of notating this that might simplify the information a little bit is by telling us really the information we need to know is where do the bits switch from ones to zeros in the subnet mask. And so in this example, you can see the decimal version of the subnet mask is 255.255.240.0. That means we have an octet of ones, a second octet of ones. That 3rd octet has 4 ones, 4 zeros, and the 4th octet is all zeros. So if we were to count up all the ones, we have 8 in the 1st octet, 8 in the 2nd octet, 4 in the 3rd octet. So 8 plus 8 plus 4 gives us 20. So we have 20 bits that are ones, 12 bits that are 0 because we have 32 bits. So all we really need to know is how many ones are there, and then we'll also know how many zeros there are. So there's another notation for this called cider notation or slash notation. In this one, all that we need to do is just say, here's how many ones there are. And then we can infer from that how many zeros because we know that there has to be a total of 32. So the CIDR notation can be a lot easier to work with. Again, instead of writing out 255.255.240.0, we can represent that as just /20. It's much easier when doing configurations as well because it's a lot less characters to type in there. So, um, so far we've only really discussed the definition and the structure of the subnet mask. This is all necessary information before we can start to understand the purpose of the subnet mask and how it functions.